You might think we're a broken record talking about subtomograph averaging for the past three sessions, but there's a reason for that. We want you to really know all the techniques out there. And given that people learn differently, it's good that you get more than one different view. So Alister Burt is coming from Genentech, and he'll give us, I guess, a guide through, I guess, Cryo-ET, subtomograph averaging,
Yeah,
everything. Life universe and everything, I see. What is your favorite part of the workflow?
I really love it when you get to, so the geometrical aspects of tomography, like you have 3D pictures, and then often leveraging that geometry in your system is the difference between whether or not your analysis works or not. And so thinking about problems in terms of, just a little bit more smartly than maybe the software puts the solution in front of you for, and then that taking you to the next level in terms of what you can do. And I've got an example of that. So
you know, now I think about it, like we should coordinate. Like Laura, you should have used 42 tilt series, 42 micrographs, because that would be the correct answer.
All right, hi everyone. I'm really happy to be here. One of the things that I love the most about still being in a scientific career, even though I've moved into industry now, is that I still get to have connections to the academic world like this, and hear about what's going on. Hopefully, see people still using tomography, and then also that we get to distribute software that hopefully some of you guys will use and might be useful for some of your work. So today I'm going to talk about Cryo-ET, both theory and practical things in the software that we develop now. And here are some nice pictures from things that I've been doing over the years. Anyway, so I'll do a quick intro to myself. My name's Alister. I did a PhD in Cryo-ET, started out as a user, so like most of you, did not have a big computational background, anything like this. The lab part of my project happened to be quite easy. The computery part of my project happened to be quite hard, and now I work at a computer all of the time, and I develop the software that you guys use. And so if you currently think of yourself as not computational, don't worry, there is hope, but it might be hard. You spend a lot of time bashing your head against the problems. I then moved back to the UK. I did a postdoc in Cambridge in David Barford's group. And then like 18 months ago now, I moved to Genentech, and I work with Dmitry Teganov on Warp and M and then future iterations of this sort of software stack. I like Cryo-ET, I like averaging, and my favorite thing to do in scientific work is enabling other people to do cool biology. So like I'm not super passionate about any one particular biological system myself, but I really do love when other people are and when you can help them get there and answer the questions. So that works. And then on the more technical side, in case any of you want to chat about things, I really like scientific visualization. And I really like, what's the other thing that I've written here? Python and the open source world in general. I think this is a really special thing that exists in the world. It's how my skill set grew and got built. And so I try and continue contributing time and effort in that space because I think it's really valuable for the world. It's one of the least transactional parts of the world that still exists. So I work in the Cryo-EM team at Genentech. I was quite surprised because I thought industry meant that everything was done at an industrial scale, but actually the Cryo-EM team itself is about 6 or 7 people in a 13,000 plus person company on site just south of San Francisco. So the team was started in, I think, 2015 by Claudio Sferi. It's now run by Alexei Rohu, who you guys might know from things like CTF Find and System. We've got Matt, Kaylee, and Chemek, who work on the sort of more facility side, running the microscopes and making sure they're performing as well as possible. And they also do a lot of sample prep and a lot of data analysis. So it's not just a run the microscopes kind of position. It's really a full, let's give this department and this company Cryo-EM as a solution kind of thing. And then Dimitri and I work on the software side. He has this set of packages that he's been working on now for 10 plus years. I've only joined more recently. And then, we've got a few microscopes. And if anyone has questions about the transition or what it's like working in industry and anything like that, we can talk tonight or throughout the day. I'm around. So today, I'm going to do a bit of theory first. I separate out theory and practical. It's like, this is the way I think about things and the way that they make sense in my brain. Hopefully, they will also make sense in your brain if they don't already. Then the practical, it's very important. It's very easy to get stuck in theory land and just say, I understand, and therefore everything should be easy. No, the practical reality of doing these things, you need to know what tools are available to you, how to actually use them, and how to solve the problems yourself. And then I mentioned just before, I'll give an illustrated example of where thinking a little bit more and going to that effort of doing something a bit more custom with your data analysis really made a difference in my own work. And so without further ado, let's start on some theory. I don't need to do this one because you've been doing a cryo-ET workshop for multiple days, but in a microscope, we collect multiple images. Typically, we rotate the sample around a single axis. This gives us multiple projections taken from different angles. Fantastic. In terms of the different data types that we will be working with, both well, in general in any software package, and then throughout today, I'll refer to things with this sort of nomenclature. So we've got multi-frame micrographs or movies that come off the microscope. So these are single 2D images separated out over time so that we can resolve motions between those frames that we collect. Then we've got tilt images. So these are single 2D images per tilt angle within that tilt series that we talked about before. Once you've assembled these individual 2D images into a stack, we tend to call it a tilt series. This is the thing that you look at. Despite looking 3D, it's important to note that this is a series of 2D images, and that is a fundamentally different thing from a 3D image, a tomogram, that we have on the far right there. And so those are the things that we have. Excellent. I hope none of this is new. If it is, I hope it's useful. Okay. When we're doing structural work with cryo-ET, what do the workflows tend to look like? We've heard different things about different software packages that are available. I like to keep things very simple, and this is very much focused on the structure land, not so much on the segmentation and statistical analysis kind of side. Pre-processing, everything that is involved in going from the raw 2D frame series images that come from the microscope all the way to these 3D reconstructions of our tomograms. I class that as pre-processing for structural workflows. Then once you have your tomograms, Jake already mentioned this morning, a lot of work goes into this annotation step. So how do I get to a set of initial particle poses and reference structure? Keeping this explicitly separate from the process of then refining those things, I think is a useful mental model, because often a lot of work goes into this middle step, and then once you've figured that out, that is the key, and then the refinement is actually quite easy. So treat it as real work and a very important thing, and think about this step in the middle a lot. Okay, apparently we have the same slide again. It's going the wrong way. Okay, fine, we're good. This general idea, tilt series processing is a superset of frame series processing. Have any of you heard this before? Does this resonate? Okay, so lots of people who come to tomography, I think this is less the case now, but it used to be very true, come from single particle land. And single particle, everything is very workflowified, everything is very well understood, and we know exactly how to get the best reconstructions out of this data. And the data that we have in single particle is fundamentally very similar to the data that we have in tomography. We have projection images taken on an electron microscope of a thin cryo sample. Okay? And so if we think about tilt series processing as frame series processing, but with a few extra things that we need to keep track of because we've imaged the same area of the scope, area of the sample in the scope multiple times, I think it's a useful mental model and lets you understand why we have to do things in certain ways and how to do them better in some cases. So yeah, tilt series processing is a superset of frame series processing. So I'm going to go back to some theory for frame series processing, and hopefully this will be useful for grounding us when we then build up to tilt series. So we have three-dimensional objects. In this case, we've got a ribosome, and I'll wiggle it around a little bit just to show you it's 3D object. A useful concept, if you haven't, you're not used to thinking about these things, it can feel a bit alien, but I promise it's nothing magical. There's an alternative representation of 3D objects, which is the 3D Fourier transform, where information is arranged as a function of spatial frequency. So as we look at the center there, where the Fourier transform is very intense, this is our low resolution information. And then as we move out to the edges, we have high resolution information. This is very similar to when we think about sheet music. You have, we don't think in terms of waveforms of the sound that we have. We think in terms of the frequencies of the notes that make up the sound that is playing at any one moment. And sometimes when we're doing the image analysis, it's useful to think in terms of the high and the low frequency information. Maybe we trust the low frequency information more in our images than the high frequency information because it's less noisy in those regions. Okay? So, how do we get between these two different representations? There's a very simple, well, not necessarily super simple, but there's a thing that we can just abstract away into a black box called the fast Fourier transform, and it will take us from 3D object to 3D Fourier transform. Now, we collect projection images in the microscope, and you might have heard of this thing called the central section theorem, Fourier slice theorem. Is this new to people, or is this, we feel okay with this? Just getting a sense. Okay, and so on the right here, I have one slice through that 3D Fourier transform that we were looking at before. And then if we look at that slice there, just like in the XY plane, and we do the inverse Fourier transform to get back to the real space, what we will have is a projection through that 3D object. Okay? And if we look at this in 3D, it still makes sense. You have information that tells you how the object is changing in two directions, but it doesn't tell you anything about how it changes along that projection direction. You have no information about how density in your sample changes along Z, that projection direction. You have lots of information about how your sample density changes in the XY plane. Make sense? Okay. And it's cool to see these things lined up. I enjoy this kind of understanding. And then, yeah, the core thing that you need to know is that we have ways of going between these different representations. And so if we can collect up these individual projection images, so these individual slices of information through those 3D Fourier transforms, then we have a way of constructing the 3D Fourier transform and therefore the 3D object that we were imaging in the microscope. Magic. We all understand. Okay, and so single particle analysis is the process of determining the shifts that you need to apply to each particle image that you have, the relative orientations of those Fourier slices as you build up the Fourier transform. And then because we're imaging in an electron microscope, there's also this set of electron optical aberrations that we need to correct for. And so defocus is the main parameter that dictates the form of those electron optical aberrations, the contrast transfer function. And so we also need to know the defocus associated with every particle image. And so once you've done this, you can build up a nice high resolution map of your 3D object that you were imaging and taking all these 2D projection images of. Anyone lost? Feel okay? Any questions? Good. Okay. So now let's do the exact same thing, but for tomography, because we're all here to do a Cryo-ET course in New York. So in this case, we are typically imaging more complicated samples. And so rather than looking at isolated proteins in a buffer solution, we have our nice complicated piece of biology. And we can't directly interpret those single projection images of more complicated samples because you've got things overlapping in the projection direction. And so what we do instead is we take multiple images of that sample. The typical collection geometry is plus minus 60 degrees around one axis. And yeah, this is an example of a tilt series that we want to collect on the microscope. We then do this back projection. And so we talked about these 3D reconstructions before in terms of how they're implemented in Fourier space. We insert these central slices. Typically, we think about tomography reconstructions more in terms of the real space back projection. These things are fundamentally equivalent. The real space one is just easier to implement more efficiently for large volumes coming from the full 4K by 4K images that come off your microscope. And that's historically why people think about these as a little bit different, despite them being the same 3D reconstruction operation. And so Once we have done this back projection step, we have the 3D image of the sample that was in the microscope. Hopefully it's all nice and crispy and you can see all the interesting biology that you wanted to look at. The next step that we need to do is we need to localize our objects of interest in that 3D volume. And so in this case, I've made it nice and simple. We just have ribosomes, and I just said, okay, we're going to click, 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 a bunch of these little guys, and nice, done. Great. Because we know the geometry that we use to do that 3D reconstruction from the 2D images, it's relatively easy actually to project those points back down into the correct position where that information came from in each 2D image in the tilt series. And so it's not exactly the same set of points. I'm sorry, I didn't do this carefully enough. But when you project those points down, you can see we have points centered on each of those little ribosomes in the tilt series. And what you can do then is you can extract a little mini particle tilt series around each of those points. And what you have there is a set of 2D projection images, and you already understand the relative orientations of some of those. You understand the projection geometry, therefore you understand the relative orientations of the Fourier slices that you would have. And so you can start to do little reconstructions of just these objects of interest that you've identified. And when we do a 3D reconstruction from these particle tilt series, single particle looks like this. And so you can't really see the slices resolved after the compression of the animation here, but you can see quite clearly there's this missing wedge of information. We just have plus minus 60 with 3-degree increments, I think we did here. And then it doesn't take many particles at all before you've completely filled this in now. So before in the single particle case, we were building up this transform 1 image at a time. Now we're building up sets of 40 images at a time. And so, yeah, we build it up a little bit here, and you'll just instantly see almost perfect reconstruction. Because this is all simulated and because this is all high signal to noise, it's very, very, very easy. So subtotal averaging, exactly like single particle analysis, is we determine the 3D shifts that center the particles really well. We determine the relative orientations of those sets of particle images in this case. So you align the particles to some common reference. You still need to know for each individual image the correct defocus because it's still an image from an electron microscope and has that CTF in it. But fundamentally, this is really not that different from the single particle analysis case that we were looking at before, right? It's fundamentally same thing, just sets of constraints. And you guys did this yesterday in Next PYP. You saw really nicely that, yeah, once it's all there, it all does work and it does make sense. Okay, so I hope I've convinced you of this little thing, like tilt series processing, frame series processing, basically the same thing, not that difficult. I really like this quote. There's a lot of value to be created in uncomplicating things that people have been complicating. Tomography is not that difficult or not that hard. There's a lot of history and a lot of people using existing software packages that weren't designed to do things. And that is what is making your life more difficult if you're trying to be a tomography practitioner these days. But hopefully it will all get easier over time because it's already been solved for single particle. I'll also do a quick parenthesis on how we deal with the CTF in tomograms, because this is a thing that people talk about and they use terms like 3D CTF, and I just think it's not always 100% clear what people mean when they talk about these concepts. So the CTF, I won't go into too much detail, but electrons that scatter at different angles have different path lengths, and then when those things refocus, they constructively or deconstructively interfere at different spatial frequencies. Grant Jensen has a really nice video on this if you want to go and follow into a little bit more detail. But the main thing that you need to know is that as the defocus parameter changes, the shape of this CTF changes a lot. And so as you go to higher defocus, you get much faster oscillations as you move to higher spatial frequency. And what I mean there is as we move from the center of the Fourier transform, this low resolution information, out to Nyquist, the highest resolution information we have in our images, we will have more oscillations of this sinusoidal function that oscillates faster and faster as we get to Nyquist. Okay, so Compared to single particle analysis, where we have these very thin film samples that we put in the microscope, we are typically working with thicker samples. And this means that we can't make some of the same assumptions that they tend to make in single particle. So in single particle, you might be able to get away with saying this whole image is at 1 micron defocus, let's say 2 microns defocus. In tomography, because the sample is much thicker, it's not safe to assume that all of the particles in your 3D object that you're imaging in the microscope are actually at the same defocus. And so how do we deal with this? Well, we say, okay, I have estimated a single defocus value from the CTF that I've observed by looking at the power spectrum of the image for this one projection image. And then I know where my different particles are in Z, right? And so here we have 2 particles. We've got yellow particle, pink particle. And if we say that in the center of the reconstruction, we have a particle, we have a plane that we estimate to be at 1 micron defocus, then as we move up, we would shift that by the physical distance that we've moved up. We'd say, oh, we're at 3.01 microns defocus. And as we move down, we would say, oh, we're at 3.-01, so 2.99. Yes. And then as we rotate the sample, we just do the geometry and look at how things change. So here I've done a very simple 90-degree rotation. And what you see is those particles that were at different defoci just before have ended up, after rotating, at exactly the same defocus. And because we, again, understand the projection geometry, we can know and back calculate all of these correct deltas that need to be applied to that one defocus value that we typically are able to measure per image. Does that make sense and feel somewhat clear? Okay. I'll move on to some software workflows. How are we doing for time? We're good. We've got some time. So, Cryo-ET, it's historically been a bit of a mess. I started doing this stuff in 2017-ish, I think, 2016, 2017. And things have got better in some ways. They've got worse in other ways. I like to call what we used to have as the patchwork elephant of pieces of software. And it was your job as someone trying to do tomography to construct the patchwork elephant. This is a slide from this review that was done by Kendra Lee and Misha Kudryashev years ago now, showing what these workflows used to look like. And it was really a case of manually stitching all of these pieces of software yourself together. Thankfully, we're not having to do quite so much of that now, but that doesn't mean that things have got easy. So things are slowly improving. We have various software packages now that are all capable of they all implement some version of this workflow. They each have their own advantages and disadvantages. They are each very good at certain things, more limited in other ways, depending on what the focus of the software developers who were working on these things was at the time. The question I'd like to put to you guys today is, there's a very obvious trend in all of these packages towards very complete solutions that try to solve all of your problems for you. Now, the reality is that we know that, let's say, Relion is very focused on structure and doing subtomogram averaging from these things. It doesn't try and help you with your segmentations or your denoising, really, in those kind of ways. WarpNet, similar, very focused on the output being structures. Other people much more focused in this analysis of the tomogram itself, getting segmentations, identifying individual components, and understanding spatial relationships. And so I worry a little bit about this tendency towards all of these pieces of software trying to do everything and not doing any of it, not being able to do all of it well, because doing all of it well is such a huge job. Maybe I'm wrong. Maybe, we saw yesterday, I was super impressed with NextPyP. They have done a great job of integrating lots of these different methods with their own solutions and providing that in a nice usable format for you guys. But I don't think I truly believe that any one software package can ever solve literally all of the things that you might want to do with tomography data. The complexity of the biology that you guys are looking at is super, super high. The number of specific things that you might want to do is nearly infinite because of that complexity. And so I don't know that we can ever realistically expect a Rely On or a CryoSpark or a whatever to actually solve all of those problems for you. And so what I advocate for personally is we skill ourselves up a little bit and we empower ourselves to solve the little problems that are specific to our data set. And then we rely on these workflows only for the specific things that they are good at and need. And so I'd like it if you'd come away with this idea of, oh, I am the scientist, I need to solve my problems. I'm not looking for a piece of software that maybe does everything. These pieces of software do specific workflows really well, but maybe I need to do a little thing myself, and that will be the difference for my project. Okay. So, yeah, this is what I just sort of ad-libbed on, and hopefully you have understood. Yes, that's the idea. Okay, I'm going to go now and talk more about the Warp and M workflow, which is what I work on now. The reason that I work on this now is actually probably because during my PhD, I was, like a lot of you, trying to explore the space of available softwares and figure out what worked. I got various things working to various degrees during my PhD, and the one that I really hit on that I finally felt like it made the easy things easy and let you solve the other things yourself was this Warp workflow. It didn't quite work for my project, so I had to add some custom things and little extra workflows around it. But overall, this workflow that Dimitri presents between his software, Warp, Rely On for doing 3D alignments of your particles, and then M to go back to the tilt series and refine that projection geometry and really figure out, wiggle all the particles into place so you can get a nice high resolution reconstruction, works really well. And yeah, I became de facto tech support because it took me a lot of troubleshooting and effort to get this workflow up and running for my own projects. And then, yeah, I've been doing more software development since, and now I get to contribute to that effort in my own day-to-day work. So, kind of nice. Briefly, I'll explain what the different components of this system do. So you've got Warp, which does that whole pre-processing block that I talked about before, motion correction, CTF estimation, particle picking. It doesn't actually have its own solutions for tilt series alignment, very similar to NextQIP that we saw yesterday. We rely on iMod and RTOMO for this. We would love to have something that was a little bit more robust than those things. We don't find that they solve every tilt series as well as we might hope to, but that's just not the case right now. So we've integrated these external solutions. Then we output particles once you've picked them, either using our template matching or your own solution for particle picking in a format that's compatible with Rely On. And once you've got your initial alignments back from Rely On, or you've maybe done some classification to get rid of junk or figure out different sets of 3D objects that you have in your sample, you can pull them back into M, which will do this process of aligning everything up and making sure that you've got the best possible reconstruction from your data. And so Warp and M, particularly Warp on the desktop, had this really great GUI. And one of the reasons I really liked using it was because I felt like you could finally see all of the information that you needed to be aware of while you were analyzing the data. And it felt really nice. Dimitri put a lot of effort into making this look and feel great. The problem was that they were locked in this Windows cage. I don't know about you, but I was sat there, I had a Windows laptop with a mobile GPU in it, and I had an external hard drive dock, and I would plug the thing in here, and then plug the thing into the Linux workstation and move things around. This trying to work between Windows and Linux was clearly not a long-term good solution. Historically, the reason Warp was developed on Windows is one, because Dimitri was comfortable in that ecosystem, and it's where he did all of his programming previously. But two, the microscope PCs have Windows on them. And the reason Warp was developed as a Windows desktop app was so that it could run alongside data collection on the microscope and visualize everything as it was coming off, and hopefully let you change your collection if you saw that things weren't working. And so he wasn't just trying to make everyone's life really difficult. There was some sense of sanity in this workflow. More recently, so in the last year or so, we've now released Warp, what we're calling Warp 2.0, which is now available on Linux. this is great in some ways because it means that people don't have to be on the Windows computers, and if they want to, they can script around and test multiple things at a time in a way that they didn't used to be able to. You also don't get the nice GUI yet, which means that unfortunately you're relegated back to the command line. So the workshop that we're going to be doing today is using this command line warp experience. I'll also show in a little bit, we're not expecting people to stay at the command line forever. That's not the long-term plan. This is a kind of let's get set up for the future move. But yeah, that's where we're at now. And hopefully you guys are willing to not have a nice web app for today's tutorial. Oh yeah, and if you want to install it, hopefully when you see the word Conda, your eyes don't glaze over and think, terrible. We've tried to make the process of installing and using this package very easy. And if anyone has any problems with those things, please do reach out on the mailing list. I will help you get this set up. I care about these things being easy to do for you. Yeah.
Is online as well?
Yes. Okay, so just in terms of the things that M can do, the big result that M got was this visualize the drug directly in the active site of the molecule, in this case a ribosome, chloramphenicol, inside a cell. That is obviously extremely cool. It is the epitome of what we could, in the best cases, hope for tomography to be able to do. Whether or not that's a reality for your own projects and for projects that we do today, very much depends on the specifics of your sample. Is the molecule flexible? Are you able to collect really thin lamellae of your complex piece of biology? But in principle, this is possible in the best cases, and hopefully we'll be able to, by improving methods, continually expand the set of things that this is possible for over time. The way that M does this is by building up and optimizing a model of the whole system. And so in M, you can have multiple different objects within this 3D space, within your 3D volume. M tries to really precisely model where all of those 3D objects are. You can even set it up to resolve that position changing over time if you want. And then it will try and optimize the shifts that align those images. It will try and deform those images a little bit to wiggle all the particles into place in case a rigid motion doesn't fully get them there. The rotation parameters that for that projection model that we were talking about, which projection direction did this image really come from? Is it what the scope said? Is it what the scope said plus 0.01 degree? That gets optimized. This image warping that I talked about, we've also got, you can't fully represent a three-dimensional warp of an object in terms of just deforming a 2D image. And so we also have this volume space warping, particle up here moves this way, particle up down here moves this way. Can't just warp those two back together. And then for frame series data, so M really tries to embody this tilt series and frame series of the same thing ideology. And so you can do both in there, although people use it much more for tomography data processing. In frame series, you can model this thing called doming, which is this idea that as you expose your thin film sample to the electron beam, it deforms like this. And so the particles in the center will move just straight up. Particles, as you go further out, will start to move out a little bit. Defocuses will change because of this deformation. So on this Linux version, we've benchmarked things. This is just an old result on some apiferritin data. It works as we would expect it to. So from just a couple of tilt series, what we'll do in the workshop today is get a nice high resolution apiferritin from very little data. We've since done higher resolution internal data sets on apiferritin and ribosomes and things, and it seems like M is performing just as well on Linux as it did on the Windows, and you don't have to use Windows anymore. So that's great. In terms of, the absolute limits of what M can do, I think it still holds resolution records in terms of both what's capable of doing with in situ data. So that people have taken on lamellae. There's these really nice sub-3 angstrom ribosome structures that have been coming out now. People have been looking at translation elongation cycles and starting to use it to understand cool biology in situ. So that's really fun to see. And then people who care about resolution and EM a little bit more have been really trying to push their apoferritins as far as they possibly can. And so the highest one that I know about for tilt series is this 1.5 in vitro apoferritin from Hitchhikers team. Analysis was done by Martin Ober. And then for frame series, not many people know about this result because it's not been published. But Dimitri pushed in vitro apoferritin from the data set that Holger Stark's lab took with the CS-corrected Titan microscope. He pushed this all the way down to 0.99. My understanding is that the reason that he didn't publish this or push to publish it was because there was some concern, why don't you see the hydrogens in this map? If it's really at 0.99, you should start to see hydrogens resolve. Why don't you see them? What he thinks, I don't claim to really know whether this is true, is that the images were not finely fractioned enough dose-wise. So I think they were collected at about 1 electron per angstrom squared per image or per frame in that frame series data. And that means that by the end of the first image, that's already blown out, and what you see is the average of that exposure. That's what he thinks. It's still a cool result. It's really cool to see the atoms separated like that. Yeah, very good. We have documentation online for people who like to read things. I know I wished that the documentation for various pieces of tomography software was much better than it is or was historically, and so I try to make it so that the documentation that we provide is good. I understand that this is not the way that everyone learns, and so I also think that putting workshops like this on is really important so that we can give people the confidence to really get going with these pieces of software and hopefully start using it to do some stuff. And so, yeah, we've already done a couple of these. We haven't publicly released the software fully because it's still missing a few things on the frame series side, but we're happy with people using it. People are getting nice results, and so we do want to start sharing it more widely, and that's what we're doing today. Okay, time-wise, we still have time. Great. I'll talk a little bit now about the future. So, much like the guys have been doing in Alberto's lab, everyone wants to be on the web. I really liked Abby saying that I could launch a couple of jobs before lab meetings so that I have something to show in my presentation. This world is clearly a lot better for all sorts of reasons. It will hopefully be a thing soon for Warp and M. I'll show you some of the progress that we've been making towards that now. The reason that we're not running this software in the workshop today is not because it's not in a place where we could do that. In theory, we could have rushed and had a thing that would have been able to run every step that we're going to do today, but we're not comfortable enough to release it yet. And so why teach you something that you can't yet use? You will learn all of the things that you need to know, doing it from the command line, the way the system works and how the different pieces interact. And then hopefully when this comes out, you'll be like, oh, yay, I'm well positioned to use it. So this project has been a kind of long-standing thing for Dimitri. It's been going on for a while, since before I arrived at Genentech. And then he got rather frustrated with how it was all going over the Christmas break. He was on vacation in Mexico, I think. And he pulled the whole thing down and rewrote it from scratch, which is, it's a move. I really respect it in lots and lots and lots of ways. And the project is definitely in a much better spot now. So we can all thank Dimitri for having gone to that effort. And yeah, hopefully we'll be in a spot to release it soon. So the system is called Relay. It's a web GUI like you might be used to. And you can log into it. So it has a whole kind of user system like you might expect. Once you're in, you can see all of the different projects that you might have. And so in Relay, a project is this very long-running thing that might have, hundreds of data sets from even multiple PhD students or grad students that work on something over a really long time. We work in a pharma company. These things run for a long time, and you need to be able to organize those large-scale efforts within a system like this. And so this might be something like a PI's long-running interest in a particular biological system would be under one project. And so here, Dimitri makes a project. If you can't tell, he was very proud of the emoji integration that he had to put a lot of effort into doing for technical reasons that I won't bore you with, but the emojis work, and you will see them throughout, and I don't know whether they will appear in the same form in the final release, but for now, lots of emojis everywhere. Within a project, we then have a sub level that you can organize things into that we call a space. And so what this practically is like one space on disk where, say, multiple data sets, we work in a pharma context, and so maybe we're doing like multiple compounds in a series that we're looking at, something like this. This might be one PhD student's work on a thing over a couple of years, or you can organize things however you want. This is it's just you have another level within projects that you can split things out into, and all of these things will be co-located on disk. And so that's how that goes. And then within each space, you can have as many of these things called views as you want that we organize things into. I typically think of these as like you're processing one data set, or you're processing one object that incorporates multiple data sets, maybe. One block of processing that, say, might lead to one or a set of structures that all go together in a publication would probably end up in a view. That's the organization. And then once Dimitri is in this view, he imports a frame series data set, so sets up the parameters and things that he needs. Once that's imported, you can start a job. I don't know. This is the process of creating a job from that. And so it might look very familiar to some of you. There's a good reason that lots of these things look this way, is because it's very convenient. You in this case create a motion and CTF job. That's typically how we start processing, and we've just blocked these pieces together because they make a nice logical block. Once the job is running, you can see running statistics for how things go, or you can see some live updating status of the job, how long it's been going on for, whether it's waiting in the cluster queue, these kind of things. You can see how the cluster queues are doing. And so here, we only have this one job that we are running right now, but you can see which queue it's in, how long it's been running for, and if the queues are really backed up because, say, the cluster is down or something's jamming them up, whatever it is. You have this overview tab for viewing those things. You can set up various cluster queues that will, it depends on, the heterogeneity in the way different people's computational infrastructure is set up is very large. And so it's very difficult to make a good solution for everyone. What we do here is we just say, you guys whoever sets up your installation of this application has some responsibility to set up that particular interface, and we provide a nice little GUI for doing that within the application. So in this case, we are submitting jobs to a high-performance computing cluster. These could also just be locally running on one machine if you have workstations, or if your company is a cloud company, you could go to the effort to get it set up there. There's no fundamental reason any of these things don't work, but this is the interface we provide. And for most people, that is flexible enough and we'll get them going, but it might take a bit of setting up in the first instance. So let's have a look at that motion and CTF job that we were looking at. It might look familiar if you were used to the old Warp desktop GUI. Dimitri has a very good feeling for how these things should feel and what the right amount of information is to expose. And so here, as you can see, as you look at individual items that you've been processing, you can see the relevant data processing information for those items, and look at that particular image, just a quick overview. And then if you click on any individual image in that bar up at the top, you get some more detailed analysis. So you can see this CTF quality fit. In this case, the pixel size is really small, and so it only fits to what looks like to not very high resolution, but that's actually quite high resolution in this case. Don't worry about it. And you can look in detail at your images, zoom in, zoom out, filter them a little bit. Then when you get to processing tilt series, we have this nice, once you've imported all of your tilt series, you can quickly view the tilt series either from this overview panel. You can select and deselect entire series or individual images within a series if you need to, and then see statistics for each of those images within the series and how everything kind of comes together. You can run all the different job types that you might expect. So here's the tilt series alignment job, in this case with eTOMO, and what the parameters, well, not parameters, what the output results look like for each tilt series here. And then if you click on an individual tilt series, you'll get more detail. And here you can even see what the tilt series looks like after having been aligned by eTOMO in this case, how the shifts look for each image, and then there's even this overlaid tilts thing when you have fiducials in a tilt series. You can tell how well your tilt series alignment has gone by whether or not the fiducials track perfectly in this in the X axis, and so they should stay at the same height in Y and just move like this. This allows you to see this. Tomogram reconstruction, and there's a way of visualizing simultaneously the three ortho slices through the tomogram for any position in the tomogram. So it's quite nice to be able to look at all these things through the dataset. You saw similar features yesterday in NextView IP. And then this is an example of what things look like when you're running in a refinement job. This one's in dark mode. Dark mode is a thing for people who like dark mode. I'm not a particular fan of dark mode, but yeah, it's great. And then you can see, how the volumes change and how the set of orientations that occupy each class changes as you move through. And we know the types of things that we like to look at and would want to have access to when thinking about how you make the next steps in your processing workflows. And so we've tried to surface as much useful information as possible. And if and when this comes out, we'd be open to feedback if you think that something is missing or not quite there that you might like to see. Very good. Just going back to this point, tomography is still hard, right? I have spent various amounts of time helping people get up and running doing tomography and trying to get going with all these different software packages and things. I think it's super important that people know how difficult it is, just because the best results from labs that have been doing this for a long time and have lots of experience are now very good. Does not mean that things will be easy for you or that enough effort has gone into making this easy for you. That's definitely changing now, but I think it's really important to acknowledge this. And then, Dimitri took this picture out in San Francisco. WN trash. Kind of funny. Okay. Good. We're going to be about on time. Glad that's worked out. I'm going to take a quick step back and talk about this thing that I mentioned at the beginning, which is we've talked about the whole workflow and how things fit together within Warp and M specifically. I'm going to give an example of where going beyond that made sense and provided some value, so that you think to do this kind of thing for your own project if it's necessary. That could be at the picking stage, that could be within the refinements, whatever it might look like. So when I started my postdoc at the LMB, I joined this effort with two really fantastic scientists, postdoc Tom Dendoven and Stan, who was a PhD student at the time. They were looking at these spindle pole bodies purified from yeast. It was work that was historically done by John Kilmartin, who's been doing this stuff for years and years, and now we have tomography, so we can look at them all at once at high resolution. It's really cool. They were trying to average at the tip of these microtubules where they attach to this spindle pole body. There's this complex called the gamma tubulin ring complex, and they wanted to see it's not true in situ because they've purified out this big complex biological object onto a grid. We call this kind of in situ or something like that. It's a big complex piece of biology, and worth making a quick aside. Often the way that you make tomography amenable or make a project tomography amenable is by figuring out the way of getting your throughput high enough that you can really collect enough field series or tomograms to make it work. So we know that lamello is, for the most part, very low throughput. Maybe lamellae of a rare event is not going to be what works for you. Maybe you need to find a way of increasing the likelihood of seeing your target when you mill or seeing your target when you get to the stage of imaging. The thing that Tom did that I really liked for not this particular project on the in vitro stuff, but he was trying to do this really in situ, was did all the work to synchronize yeast nuclei at a specific point in the cell cycle, and then make sure that they were all in that same point on the cell cycle on the grid, and then extract the nuclei while keeping them in that synchronized state, and then pack all the nuclei down onto a grid, and then mill that to get thin enough samples for imaging. And so these kind of things often also really make a difference on the sample side, and it's worth taking a step back and thinking about how to get tomography done for your particular piece of biology. When I joined this effort, I'd been teaching Tom how to do subtomography averaging using the workflow that I'd put together before he joined, and he'd got to the stage of a sort of 11 angstrom-ish reconstruction of this complex, which was super cool, but they didn't see too much new. It was new in that nobody had visualized these things capping the microtubule before, but it was not saying anything that was particularly interesting at that point. The resolution was definitely limited by something because they were doing this co-refinement of multiple species in N, and the microtubules were getting down to about 6 angstroms, so there were a lot more particles there, and so we were either limited by particle number or some little bit of flexibility or some heterogeneity. I dove into this, doing some classifications at low resolution in Relion, quite quickly showed that we had different orientations of this asymmetric complex being mixed within that reconstruction. And so we had to separate those things out and then put them all back in the right place. I developed a little workflow. We like to manipulate things in Chimera. We all know that this is like where we're comfortable. I set it up so that you can just align the classes to each other. You choose one class that's your kind of fixed one, and then you align the rest of them to it, and then apply these transformations to your sets of particles in the classes that are moving. And then after having done this and then rerun a refinement in these new orientations, just locally putting everything back into place, we saw that actually this interface at what they call the seam of the microtubule over here was really cleaned up quite a lot. And they saw some specific linkage, which I don't know the biology too well, but apparently it's interesting, and apparently it was not like a thing that was particularly known about before. Really great. I like enabling biology, not necessarily going much further than that. So yeah, we did that. Then the other thing that was kind of interesting was if you looked at slices through the ice. So yeah, this is another thing. If you're not used to looking at this data, we in single particle almost always look at isosurface representations of these volumes. And actually, an isosurface is very useful, but if you have different regions of your volume that are at different intensities because you have, say, lower occupancy or some flexibility, then actually this isosurface cutting at the same density level is not necessarily giving you a great representation. So isosurfaces are only really good if you also are changing the threshold and spinning them around and all of this. But if you look at slices through the maps, you often see features that are kind of, things become obvious, what might be going on. And so here we saw at much lower occupancy than the main density of this whole complex, this little kind of appendage that looked like it was kind of bridging the top to the microtubule protofilament that we see there. And we thought, oh, this thing might be interesting, but we don't really see it in the map. What is it? What is it doing? So in this case, we have 7 of this subcomplex called the gamma-tubulin subcomplex, I guess, gammatos. Here I've highlighted it in blue. As you move around, you see the 7 different copies of this Y-shaped thing. I developed this little workflow for annotating the positions and also the orientations of these subcomplexes within your larger complex that you might be interesting. So we made the assumption that the densities around these subcomplexes that we were interested in might be similar in those 7 examples. And so we wanted to average them all together, increase our particle number, hopefully wiggle things into place a little bit better, and maybe see something interesting. We went through that process. We got this reconstruction of just one of those subcomplexes on the protofilaments. And suddenly we could see really nicely that this was actually a coiled coil protein. They then went to a lot of effort to try and identify what that coiled protein was, and unfortunately, it was not 100% sure by the time that the project finished up. But yeah, it was really fun, and I think is a nice example of going a little bit the extra mile, thinking about the geometry of your system, providing more insight that led to hopefully being able to say a bit more about the biological system that you're interested in. And so, yeah, here we increased the particle number 7 times. So we ended up with about 56,000 particles, and things cleaned up really nicely. Yeah, thank you very much for listening. I would love to take any questions, and yeah, we'll start with a little bit of workshop setup stuff before going off for lunch, I think. Hey.
So from the last slide, that was really cool how you could see that really small density kind of pop out and do the 7x averaging. Do you have any idea about like the population of that density, like within the subparticles? Do you have an idea about like the classification and kind of thing?
So we think that the reason that the density was low is probably more a flexibility thing, and because of misalignments in the global set of particles that we used where we saw it at lower occupancy, rather than an actual occupancy difference for that particular thing. So we think it's really there in all of the subparticles. And then once you have cleaned everything up and aligned and averaged it correctly, it's at almost the same threshold in the density. And so, yeah, there's an approach that was developed by Bjorn Fesberg, who did a lot of the GPU acceleration for Relion, for looking at a map. And if you have regions that are lower intensity, it will try and tell you specifically what the occupancy of those regions is under different sets of assumptions about whether or not it's there all the time or whether or not it might be also at lower occupancy because it's flexible. And the software that lets you explore this and run these workflows is called Occupy. And it has a nice feature as well of letting you equalize the density of these different things, which can sometimes help with generating, say, 2 maps where you have one at high occupancy and one at 0 occupancy to start classification and sort of push it in the right direction. Hey.
Is walk 2.0 just walk run running on Linux? So if you've like optimized parameters for walk 1, can you use them in walk 2, or do you have to kind of start over?
Yes, with a star asterisk. There's a page on the documentation which is specifically about how you go about migrating from walk 1 to walk 2. You have to redo 1 or 2 steps and kind of canoodle it a little bit, but it does work. It's a thing that you can do, and I understand the reasons for wanting to. You don't want to have to repick particles. You don't want to have to do whatever. For the most part, I recommend people to try and build experience with walk 2 first so that they don't make a bunch of mistakes when trying to do that process because they don't understand how things are supposed to go in walk 2. There are a couple of little things that are just teeny tiny bit different, and you can trip up and be frustrated if you try and get this to work without first understanding things. Hey.
The web interface that you showed looks very nice. So on that, what kind of technologies did you use to build it?
Yeah, so the web interface mostly built by Dimitri. I've contributed like visualizations and a few little components and things, and so yeah, that's his work, and thank you for those. Yeah, I agree that it looks really good. It's built in C# using the Microsoft provided version of or equivalent of React, which is called Blazor. And then he has had to build a lot of custom components for all of the specific cryo-EM visualization things that you've seen there today.
Is that running on like a software?
No, it's just yeah, that's it running in our local cluster and connected up there and everything. But
I meant like the workplace software. It's like a full Microsoft stack.
Full Microsoft stack, so the backend is all normal C# stuff. I think Kestrel is the thing that's running the server and everything, but that's abstracted a bit behind Blazor for doing that, and yeah. Cool. Thank you guys for listening. Lunch is always a good thing to go and have. Maybe if we have a couple of minutes, is the start of lunch.
We're gonna have a group photo and then lunch, and then it's actually a very extended lunch, it's an hour and a half, so.
Okay.
That people can take a walk if they need to, but then
Yeah.
be able to set up, for your track.
Cool. I won't take any more time. We can set up for the practical when we start the practical after lunch. That'll all be great. Thanks.